Hi everyone. In this video I will be proving a result that deals with the differences of points in the Cantor set, which is quite interesting. So as we've seen several times, the Cantor set is quite unusual in the sense that we sort of expect it to be quite sparse over 0, 1, since the construction and the fact that it has measure 0 leads us to believe so. However, we know that the Cantor set is uncountable, which is unusual, and I think that the following results are also equally surprising and interesting. So the results that I will prove today, just quickly, is that in words, is that the distances between points in the Cantor set fills the unit interval. Also, the addition, the sum of points in the Cantor set fills the unit interval, and the average of points in the Cantor set fills the unit interval. So these are the three main results that I'll be showing today, and they all are corollaries of a more general theorem, which is what I will prove. So let's see. So for any point in 0, 1, call it C, and also let the absolute value of m be between 1/3 and 3. Then the theorem states there exists x, y in the Cantor set such that y minus mx, let me just write that better, equals c. So for any c in 0, 1 and any m in 1/3, between 1/3 and 3 absolute value, there is a point. There are points x and y in the Cantor set such that this equation is satisfied. And now you might see right away that this equation is the general equation for a line, which might lead you to believe that this proof will be somewhat geometrical, and you would be right. And just to have a little bit of foresight, we'll see that once we've proven this, if we take m equals 1, we'll have our result number 1, because we'll have y minus x equals c. So the distances between points, some points in the Cantor set, equals a given c in 0, 1. So we can fill up the whole unit interval in that way. So we'll come back to this later. But for now, let's prove this theorem. So let's let sigma be the set of points in the unit square, xy, such that x is in the Cantor set constructed on the x-axis, and y is in the Cantor set constructed on the y-axis. So what we're going to do is construct the Cantor set simultaneously on the x and y-axis, and it'll be sort of like a two-dimensional Cantor set construction, and that's what we'll use for the proof. So also we're going to call this line lambda, y minus mx equals c, or as we know it better, probably y equals mx plus c. And the theorem will be proved once we can show that lambda meets sigma in at least one point. So what we need to do next is draw our construction on the unit square. So I will do that right here. So let's call this the unit square. Apologies for the messiness. This is y, this is x, 0. And we'll locate 1/3 and 2/3. 1/3, 2/3. So we're going to construct the Cantor set on the x-axis and the y-axis simultaneously. Recall that in each step you remove the open middle 1/3 of the remaining intervals. So we're removing open 1/3. That means those endpoints will still be on there. And it looks like the removed portion looks like a cross. So this fuzzy is the removed portion, and what we're left with is these 4 outer squares, each with the area 1/9. And so let's call the unit square, the big square, S0, and we will give names to these smaller squares shortly based on if they intersect with this line or not, as we'll see. So let's just write out a couple of observations that we need to move forward. So observation 1, the line lambda, y equals mx plus c, meets the unit square since its y-intercept, which is c, is in 0, 1. So just to go back for a second, we can see that if c is any point in 0, 1, then obviously this this line will meet S0, right? We haven't removed anything yet at that stage for the unit square, so that's obvious. But since the slope is either between -1/3 and -3 and -1/3, or 1/3 and 3, we can see that lambda, the line, must also meet one of the 4 smaller outer squares. At least one of the 4 smaller squares. Okay, so let's discuss that a little more. So let's take the most extreme case. So let's take c is 1/3 and the slope m equals also 1/3. Then the line will look something like this, if you can see there, and it's touching this smaller square here and this smaller square here. And so it's touching at least one of the 4 smaller squares. And then if we were to change c, which would bring the intercept up or down, or if we were to change the slope between 1/3 and 3, it would always still touch one of the smaller squares. So let's say, forget about c for now, and let's say this line only intersected here, let's say. So here where we have we have the intersection at x equals 1/3, and we have the slope of the line at 3. So even in this case, we see that it still touches at least one of those 4 smaller squares. And if we were to change the slope at all between 1/3 and 3, this would always be the case. It would always still touch. Hopefully this is clear right now. And so the second observation is that observation 1 is true of any square whose sides are parallel to the 2 axes. X and Y axis. So basically, what this is saying is that as we remove strips, so let's say our line, let's say, okay, so this would be step 2. We would remove strips from all 4 of these, but doesn't really matter to do all of them. So let's say the line crosses here. Then we can see that we can see that this smaller square of the smaller upper left corner square is the one that gets intersected. And because of our 2 observations, we know that we can say further that since this square is being intersected, then one of the 4 smaller squares inside remaining after the next stage of removal will also have to be intersected, and so on and so on. So let's call the first square that the first smaller square of these outer 4 that gets intersected, let's call that S1, and then the next one that gets intersected, let's call it S2, and so on. So what we're left with is we repeat this process, and we get a decreasing or shrinking, let's say, sequence of compact, because compact, which is closed and bounded squares, and they're, as we've named them, S1, S2, etc., and they're within each other, and their diameters are shrinking to 0, and they always, each one of them intersects with the line lambda. So that set between the intersection of the line and any of the squares is non-empty, and that applies to any of them. So as we repeat this process infinitely, there's a theorem called the Cantor intersection theorem. And it states that a decreasing sequence of a decreasing nested sequence of non-empty. We know that each of these squares is non-empty. Each of those sets, or whatever you want to call them, the squares is non-empty. Compact, so a decreasing nested sequence of non-empty compact sets has a non-empty intersection. And I think we've seen something similar in one dimension, but this confirms it for this 2-dimensional case. And so this leaves us with the fact that the intersection of all of these squares, n equals 0 to infinity, is non-empty. And we know that this belongs to our set sigma as defined, which is all the points in the unit square such that the x's and y's are in the Cantor set. And so now we've shown basically that this line lambda intersects intersects the set sigma, which is what we set out to do initially, which concludes the proof of this more general theorem. And so just to come back to our 3 corollaries, we've already shown that if we take m equals 1, then we have that the differences between points in the Cantor set y minus x equals c. For any c, there's some y and x where this is true. 0, 1. Now, if we take m equals -1, then we'll get result number 2. So this was 1, this is 2, and I'll show 3 after. Because then we have y plus x equals c. So every point in 0, 1 is the sum of points in the Cantor set. And finally, if we change c to 2c, c to 2c, and we take m equals -1 again, we're allowed to do this. I'll skip over the details, but basically, if you draw out the picture with 2c instead of c in the case that m equals -1, you'll see that it'll still intersect all the squares, it'll still intersect the square at each stage. And anyways, this leads us to y plus x over 2 equals c, which is the average of points in the Cantor set fills the unit interval. And that is it, I believe. So I know that this didn't have much measure theory involved in it, but since the Cantor set is so important to measure theory, I feel that these results are nonetheless quite interesting to us for the purposes of our class. So